Centre and what it can do for manufacturers. So I'm Iain Bomphray. I'm the director of the Lightweight Manufacturing Centre, and I'm joined today by Alex Cochrane and Jay Liu, both engineers working with the LMC. So some housekeeping, the webinar is being recorded and it will be made available on YouTube. Your microphones and webcams are turned off during the session to avoid background noise. Please feel free to type your questions throughout the session via the chat tool. Time will be allocated at the end for questions and answers. Also, please use the hashtag NMIS Insights for questions, and please take some time to complete the survey after the webinar. So I'll start by introducing the National Manufacturing Institute Scotland. So NMIS is a group of industry-led manufacturing research and development facilities with research from industry and public sector working together to transform skills, productivity and innovation to attract investment and make Scotland a global leader in advanced manufacturing. NMIS will increase productivity by reducing barriers to innovation, to stimulate investment and increase manufacturing competitiveness, to catalyse job creation and strengthen supply chain links, to inspire and attract talent and equip current and future workforces with the skills they and businesses need, and to work with manufacturing businesses of all sizes in multiple sectors, providing benefits across the whole of Scotland. So we refer to this as One Team Scotland. It's operated by the University of Strathclyde and it's supported by the agencies highlighted on this slide. So the NMIS group consists of a number of kind of core elements. The digital factory, the collaboration hub and the manufacturing skills academy will be available from 2021. But two specialist centres, including the Lightweight Manufacturing Centre and the Advanced Forming Research Centre are open now. The Advanced Forming Research Centre has been in existence for about 10 years and is the more mature facility. But the LMC was officially opened this time last year, and we're here today to give an overview of how that's developed in that time. So the agenda for today is I will give a quick introduction to the centre. So I'll talk about the roles and the capabilities, the staff that we've been able to attract, the programmes that we've delivered, and some of the strategic themes that we're developing. To take a deeper dive into two of those strategic themes, I'll call on my colleagues Alex Cochrane and Jill to talk about the case studies in the Reconfigurable pilot line and composites recycling and reuse. Their presentations will be about 15 minutes each, and that should leave about 20 minutes at the end for Q&A. So officially opened on the 26th of June 2019, the LMC is a pilot programme for NMIS. It's situated in a 6,500 square metre facility in Renfrew. The LMC contains a factory within a factory and has been specifically developed to incorporate a number of capabilities that will support companies moving into lightweight materials and manufacturing processes, and also academic pull-through on novel materials and manufacturing processes. The launch capabilities, we have 500 square meters of Class 8 clean room. We have one RTM press. We have one 340-ton press with heated platens to 400 degrees C, which enables us to develop materials up to the high-end semi-crystalline thermoplastics. We also have an autoclave and a Breton 5-axis machining cell, which is it's got a high specification, so we can machine down to 7 microns locally and 20 microns within the area, which is about 20 meters squared. So you can see on the map that we're situated next to the airport within Glasgow. We're about 10 minutes drive from our sister catapult, the AFRC, and about 5 minutes drive from the new facility that's being built next to the airport. for NMIS. So the facilities that we're in at the moment are temporary. You can see on the top right slide. So we're here really to get the program up and running with the aspiration to move into the new NMIS building when it opens in Q1 of 2020. So the role of the LMC really is to support lightweight manufacturing. We do that through applying different materials, methods, design processes, engineering techniques, and manufacturing methods. We're doing this to support academic and industrial engagement, as we already mentioned, and to develop the Scottish supply chain capability. And if I pause there just for a second to draw your attention to the map on the right-hand side. So this is a map that's taken from the Trade Association for Composites within the UK, and it highlights some of the registered activity in this field. You can see that, that there's a lot of activity in England and even in Northern Ireland and Wales, but the current activity in Scotland is quite sparse and fragmented, and the LMC is really here to be a focal point and a catalyst with which to help kind of develop the supply chain within Scotland, both for SMEs and primes. We do that by making proof of concepts really into helping companies who are thinking about moving into these fields and materials to come to us to discuss what the issues are, and we can help them to develop product and also the kind of business case supporting that. One of the major things we're trying to do as well is to develop skills. So the facilities mean nothing without the people really to engage with them and to develop and be able to take on those specialist skills and develop them into a context which is relevant for industry. So composite manufacturing is, well, lightweight engineering is really a holistic approach. It's not about turning everything into composites. We deliberately left composites out from the title to enable us to look at other materials and technologies, including the metals. So it's all about really getting the concept right. It's about making sure that you're using the right material, the right manufacturing process, and the right quantities. So we do that through intelligent design. We look at material selection. We're agnostic in our kind of material selection, so we look upon this as getting the right material and the right process for your needs, whether it be for high volume, low cost, or for kind of high performance, bespoke applications. So. Our staff really are aiming to provide some specialism in each of the categories that you see there in order to support your businesses. So we talk about the technology readiness levels, and really this is very much across sector. So this has been, this is a scale that we use to determine a product or process maturity, with TRL1 being blue sky and TRL9 being production ready. The catapult centres exist to enable and facilitate the development of products and processes from low to high TRL, de-risking as we advance and providing fidelity to business cases and helping organisations to be more impactful. So I think this is really a key side. We talk a lot about the valley of death, and we're really, we're here to help in various ways for companies to develop a methodical and structured approach. So some of the staff that we have here today, we will be up to 12 FTEs by the end of September. Each of these people bring their own set of skills and their own experience. I've been really encouraged by the level of people that we've been able to attract to the centre, and I think we're starting to really gel together as a team and starting to kind of work together to help deliver programs and bring our own research interests as well. And you'll see some of that in the strategic themes that we're developing now. So some of the programs that we've undertaken to date, we'll focus on two really. So we have ActBlade. So this is a Scottish SME with a big idea to revolutionize wind turbine blade manufacture. We helped them realize part of this ambition through the manufacture of a 13-meter blade on site at the LMC using cost-effective out-of-autoclave techniques. We were able to support ActBlade commercially as well through the through an Innovate UK program, which is a really good way of engaging with the catapult centres, because we were able to offer 100% funding for up to 30% of the total program costs. So with the help of our other catapult colleagues, the Offshore Renewable Energy Catapult and the Advanced Manufacturing Research Centre in Sheffield, we were able to put together a consortium of companies which enabled ActBlade to really leverage the funding that was available to them. And we produced this wind turbine blade that you can see here on the right, at the offshore, being tested at the Offshore Renewable Energy Catapult in Blythe. So that was a really successful program for us. It had enabled our staff to get really hands-on experience manufacturing these large out-of-autoclave parts. So there was a lot of learning for us and for ActBlade, and the output of that has been a very successful product, which is just completed its structural testing. Spirit Air Systems is another program which we've been involved in through the development of a spoiler within the LMC using our RTM press. This piece of equipment was brought in specifically for this role. It enabled us to support Spirit not just in product development but also with training as they get their new facility at Prestwick up and running and focused on running at rate for manufacture. So hopefully we'll continue to support in that through training and other development cycles, which otherwise would prevent them from running their production lines at rate. So if I move on to the strategic themes, so in the last 6 to 12 months, as well as delivering programs, we've also had the opportunity to really look at what's been demanded of us from a national context and start to formulate a strategy behind the support of these demands. So Alex and Jill will talk in more depth about the reconfigurable pilot line and recycling, but if I can just talk about the other ones, including the Future Materials Hub, which is an endeavour to create the next generation of fibre really from a more sustainable source. So the current feedstock for the likes of carbon fibre comes from crude oil, and we're looking at more sustainable feedstocks, including biomass, which could be wood pulp or some sugar-based derivatives. So this is a group that we've kind of brought together to help explore the development of these materials. Sustainability obviously being a really key factor in Scottish Government plans, and it fits well with our kind of strategic aims of providing alternative and innovative materials for Scottish and UK industries. In terms of large scale, we're collaborating with the University of Edinburgh to look at developing a large scale capability over in the east of Scotland within the Rosyth Advanced Manufacturing Park. So that's an ongoing development, and it's really could be quite impactful to the Scottish economy. The third thing I'll talk about today is cold composites. So this is really related to how materials behave at very low temperatures. So anything between 4 and 20 Kelvin. This is being driven by demand for superconducting in aerospace and automotive, in nuclear, and also in the space sector, which has a huge amount of potential here in Scotland with the vertical launch site up in Caithness. the burgeoning kind of satellite manufacturing capability within the Central Belt, and obviously we're looking to also acquire some capability in horizontal launch. So at that point, I'll hand over to my colleagues, Alex and Joe. So Alex is going to talk to you a little bit in a little bit more depth about the reconfigurable pilot line. So I will stop sharing now and hand over to Alex.
Thanks, Ian. To see at this point. Just to introduce myself, my name's Alex. I'm an R&D engineer here at the LMC. I'm going to take you through our reconfigurable pilot line, or RPL, research theme. I just want to take a moment to mention that while a lot of these slides focus on composite materials, and Ian's touched on this before, this reconfigurable pilot line concept is intended to be inclusive of many different technologies. So please, if you're not from a composites background, don't feel sort of left out, or that you will be excluded from this kind of project in the future. Start by reflecting on some of what Ian has discussed previously, and revisit this plot that we saw of composites manufacturing activity across the UK. And what we see in Scotland is that we've got a very fragmented supply chain. There's a sort of scatter of what will be SMEs compared to England, which has both a combination of SMEs and very large companies, and in a much sort of denser spread. So in order to help join up those SMEs, we want to do a few things. Firstly, we want to help develop their technology for them and help them de-risk that development. In particular for SMEs, we don't want to see them feel financially exposed when trying out new things and innovating around their production lines. We want to be very flexible with regard to providing technical solutions to their problems. We might see manufacturers trying to make a range of different components. So we'll be approached by different partners wanting to do all sorts of different things. So we want to be very flexible. We want to be able to produce a part, I've called it end-to-end composite manufacturing capability. We want to be able to produce a part right from the raw material through to the final component, so that customers don't have to go elsewhere to fulfill other parts of their manufacturing requirements. And I think if we manage to do all those things, then that should help to fill those gaps in the supply chain. A useful way to kind of demonstrate the different stages of a manufacturing process and iron out those problems in development is by using something called a pilot line, which many of you will be familiar with. Traditionally, this kind of conventional type of fixed pilot line wouldn't be reconfigurable, so you'd have a set of fixed machines that won't be changed out. This is essentially a smaller scale version of a real product manufacturing line, and is generally composed of sort of smaller development versions of the equipment you might see in that real manufacturing line. It involves taking, just as in the real process, taking raw material, subjecting it to different manufacturing operations in different cells that will, as I said, comprise sort of development versions of the real processes, and then we'll get a sort of scaled product or sub-element out of that. And this diagram basically shows it's an existing pilot line, and that shows the layout of it. It uses things called modules, which is just what I'm describing as cells, and that's for the production of parts from recycled material. So with all that in mind, we want to think about what would a pilot line look like for a composite part, for example. So if I could, this table initially looks very busy, but I don't want you to focus on all the detail in the table. What I've tried to do is put together 4 different paths of manufacturing different composite parts, splitting it up into what would happen in each production cell that you might find in a pilot line. So we've got an aerospace reb down to a subsea panel there. These are the different components on the left. And the main thing I want you to take away from this is that the manufacturing processes for each of these parts differ massively. So if we tried to establish a fixed pilot line for each one of those parts, which might represent a different partner company we're working with, then we have to invest massively in building those separate pilot lines. And so in order to deal with this need for flexibility, we've come up with the concept of a reconfigurable pilot line. Now, I'll call it an RPL from now on. The RPL concept is similar to the fixed pilot lines that I showed you before, where we have an arrangement of multiple manufacturing cells making up a kind of manufacturing network, a line, and performing different operations. But instead, we have a sort of portfolio of equipment in this case, in which we can swap equipment in and out into different reconfigurable cells. Now, just to describe this diagram, this is a top-down drawing of a proposed RPL concept, where the grey boxes on it are production cells. This black line is essentially the pathways that can be followed by material and parts. And the blue circles are industrial robots, which would be working with material handling between different cells and transferring material between them. Now, the building block of this RPL concept is this common, this grey box, which can be cloned and basically functions as a module within a greater network and can be very easily swapped in and out of that network and has a common interface with that to facilitate that. And it can be swapping out can be done with very little impact on the rest of the network. And each of those cells has a unique capability in terms of the technology it uses, but it's integrated with the rest of the network. So, for example, we could look at things like enterprise resource planning for this network to look at usage and downtime of each different cell. But the main thing we're looking at is how the cells would speak to one another to have a truly sort of smart, reconfigurable pilot line. And this arrangement would be highly automated, so we'd be looking to remove humans, sounds more sinister than it is, from the manufacturing process. Generally, if we look at composites in this example, humans are generally involved in a lot of the manufacturing processes there, and that often is in a hazardous environment with hazardous chemicals, and also introduces variability because we often depend on the experience of an operator to get a good quality part. So we want to remove that. And some of this we envisage making up this RPL are things like automated fiber placement, hot pressing of material, automated ply cutting and composite machining. We actually already have a lot of that capability at the LMC, and we'll be looking to leverage the entire capabilities of the National Manufacturing Institute Scotland for this, and that includes advanced metal forming as well. Now, what this does is open up the opportunity for us to not just look at the specifics of maybe a single process for a particular customer, but look at their entire production line, which is really useful for looking at things like production rates and connectivity of that line. And lastly, just on this slide, I just want to point out that this really isn't limited to composites. What we want to aim for is working with all sorts of materials, things like hybrid structures, and are always open to ideas. As I said, it's a modular system, so we'd be very open to inserting new technologies into that. Explain by way of an illustrative example how this would function or why it's needed. If we have two hypothetical products, A and B, both are different products, and they each have to go through a manufacturing process. So for product A, maybe it's an aerospace panel, and to input to that, we have carbon fiber prepreg. It's very, very common material to put into that process. That would have to go through some sort of CNC ply cutting. We would then lay up those plies, probably by hand at the moment. We'd be looking to automate that. It would then go into a mold and be autoclave cured for about 10 hours. We'd come out, be trimmed, and we'd have our scaled component at the end. But if we then change that to say that we want a glass fiber domestic wind turbine blade, for example, okay, then we're putting glass fiber, dry fiber into the production process as our input material. We then need to cut that using a different process from the prepreg because that will release harmful kind of dry, loose fibers into the atmosphere, for example. It will generally be laid up by hand at the moment, and a binder to have to kind of stick those plies down, and that will take place in a mold that is meters long. Then we'll use a process called resin infusion, which may take days to infuse that preform with resin. Then we would take that out, debag it, probably trim it, and adhesively bond maybe parts together, and then we would have our final part. So those are two massively different processes that really emphasize the need for flexibility and reconfigurability in this sense. But what we know is that with composites, so if we focus back on composites manufacture specifically, we're dealing with a whole set of challenges with the way that the machines that we're trying to automate have to interface with the materials that we're talking about. And that leads to a whole set of other challenges. So those are things like materials handling. A lot of composites manufacturing involves pick and place of materials, but those materials have very different properties. They can be dry, they can be wet, they can be soft or hard, thin or thick. And with composites, the automation has to know how to deal with those materials. That's previously why we've often stuck to using manual processes with our hands, because humans innately have the ability to kind of sense what they're handling. So this, for example, the top left, we have a robotic arm. This is from Linköping University in Sweden. This is how an end effector might interface with a composite ply to then apply that to a mold, and it has to adapt to the mold. We've had a lot of work done by the universities of Bristol and Nottingham in kind of trying to get the dexterity of human fingers and hands in applying prepreg to a mold. This is someone applying tension, while the robot actually applies the pressure to kind of get that into the corner radius. Things like pressure sensing are important. We're dealing with viscoelastic materials a lot of the time here, and the machine has to know how hard is it pushing. When you're doing this by hand, you can sense that innately, but a machine needs to be told what to do. And lastly, things like path planning. So if you imagine an Amazon warehouse where we have lots of little, what they're called Kiva robots, that have to move around, and they're constantly optimizing their paths to work out, how do I get from A to B as fast as possible, minimizing energy, minimizing the time I take? Can I pick something up on the way? These are all considerations we're going to have to make in a manufacturing, advanced manufacturing sort of context, which is really interesting. I want to say that what we have here is an opportunity not just to explore the actual manufacturing processes themselves in detail, but to try and look at the way that each process is connected in that overall chain. And we ultimately want the machines that are part of that chain to speak to each other, to make sure this is truly a kind of industry 4.0 arrangement where data is collected all the time and fed into the other processes in that chain and into the research outcomes that we generate. But ultimately, a key message to take away from it is that we're dealing with a lot of SMEs in Scotland and smaller companies, and for whom it's not in the best interests to be taking huge financial risks on innovating around their production lines and production systems. So for us, we want to provide a low-cost, flexible solution which allows them to perform that innovation and allows us to do our research and to further improve the service that we can provide, which will just create a kind of feedback loop of knowledge and skills to then handle more complex issues. And just to briefly touch on the I've got on this slide, this is a fully automated production line for Audi parts in Germany, and this is one in Britain for parts of a chassis, both from an automotive background. And these are just kind of state-of-the-art automated composite production lines. So we want to do that in a smaller scale, kind of development sense, but the key thing is that we want to do it and make it reconfigurable. So thank you very much, guys, for listening to me. I would now pass you over to Jill, who's going to tell you about composites recycling.
I'm sorry, I have been muted. Can everyone hear me?
Muted, Jill. We can hear you.
Oh, okay. Hello everyone. Sorry, this is Jill. I'm a composites engineer from the Light Manufacturing Center. And today I will talk about the research activities on composites recycling in our center. So the advanced composites material with the high specific mechanical properties becomes more and more popular in the recent years, especially for the aerospace, automotive, and the renewable energy industry. And this kind of lightweight material can help to improve the fuel efficiency and reduce the emissions. But within the increased interest of using the composites material, the recyclability becomes the key issue. So for example, since 2015, it has been requested that at least 95% of a new vehicle by weight need to be recycled at the end of life. and 85% of the waste should be reused. So not only because of the environmental legislation, but also to approach to the circular economy, the sustainability of the material has been used becomes one of the top priority for the automotive industrial company. On the other hand, for the renewable energy sectors, there will be 12,000 wind turbines are expected to be decommissioned in the next 5 years, which makes the recycling of composite material become critical to a broader range of sectors. So if you're still not very clear on how important it is to develop the composite recycling technology, we could have a look at some more detailed numbers. So it has been estimated by the Composites UK, there will be hundreds of tons of carbon fiber reinforced plastic waste from the end-of-life aircraft in 2020. And this number will increase to 1,000 tons within just 5 to 10 years. And for the glass fiber reinforced plastic, it has been estimated in 2018, there was nearly 100,000 tons scraps from different sectors, such as constructions, automotive, renewable energies, and also the aerospace. So we could have a look at this graph, which is telling us the weight of waste wind turbine blade for the next 20 years. So from 2018 and to the 2028, you can see this number is gradually increasing. But after 2028, it will suddenly jump to 10 times higher. And around 2035, we're achieving our first peak. Because if you build a wind turbine blade today, it will need to be decommissioned after 25 years. So all these numbers and informations are telling us we really need to think about how we can properly recycle the composite material. What are the challenges currently for the recycling industry? It can be the limited size of the market, high recycling cost, and the lower quality of recycling compared to the virgin fiber materials. And although the environmental legislation can help us to promote the recycling, we still need to think about the long-term technological developments. To solve the problem from the very beginning, we need to develop the more sustainable and greener material to replace or partially replace the traditional composite material. The research activities on this task will be developed through our future material hub theme. So if you are a material development engineer or chemist, please feel free to contact us. In addition, it is also very important to support the optimization of the current commercialized recycling technologies. For example, the very widely used pyrolysis process. And as a catapult center, one of our responsibilities is to transfer the lower TRL research work to the pilot scale or closing to the market technologies. So we would like to help in scaling up the novel food aspect recycling process. And as a research center, we should also keen to encourage and support the fundamental high-risk research work. We will work collaboratively with the academics to develop the novel composite recycling process. And in the end, it is also our role to make sure we fully understand the properties of recyclates and explore the potentials of the future design and manufacturing with recycled composite material. So to some of you maybe not familiar with composite material or recycled composite material, I will give you a short introduction. So this is very typical images of a recycled carbon fiber from the food aspect process. So lots of engineers and researchers currently working on develop a reprocessing process to convert this fluffy and 3D randomized recycled fiber to several intermediate products. So if you're working in composite manufacturing area, you may be familiar with the milled powders and the pellets. They are very easy to be manufactured by the low-cost process. And but the product value becomes very low, and although it has been widely used, but the market has been fully filled. So currently, the non-wovens and the 3D preform become very popular, but due to the random the fiber orientation, you can't achieve very high mechanical properties, and maybe you can increase to very high molding pressure, but it will lead to a fiber breakage. So the researchers start to think about realign the fibers. You can see the hybrid yarns, which can be manufactured by the traditional textile process called friction spinning process. So the format of this material is very similar to the virgin fiber products. But because the fibers are only partially aligned and there are some issues of fiber attaching, the mechanical property is not very good, and you need to spend the extra cost on the secondary conversion process to convert the yarns to fabric or performs steel braiding or weaving. So on the other hand, the aligned short fiber prepreg tools has been developed by the University of Bristol, but because the limited size of the material, it can be only applied on the 3D printing or AFP machine. So in the end, there's another novel material has been developed by the University of Nottingham. We can call it highly aligned short fiber tape. So this can convert to preform and prepreg, which can be easily engaged with the high volume production line, for example, the compression molding. So I will use this material as a case study to explain the full story about carbon fiber composites recycling and reuse. So this project has been done by the University of Nottingham and fully funded by Boeing. So the first stage, the researchers collected the end-of-life waste and do the first size reduction to make sure the pieces can be fit into the pilot scale fluid bed recycling process. And in the end of this process, you can collect the very clean and fluffy recycled carbon fiber. And a hydrodynamic alignment process has been developed to convert this fluffy fiber to highly aligned tape. So the dry mat compaction test has been done to make sure we understand on the different molding pressures what kind of volume fractions you can achieve. So we can have this green curve, which is indicating the properties of the aligned fiber tape made by the University of Nottingham and with the 3 mm length recycled carbon fiber. So on the 7-bar molding pressure, which is usually applied on the autoclave molding process, you can achieve roughly 50% of fiber volume content, which is a lot better than the red curve, which indicating the properties of commercialized random fiber mass. And the green curve is also approaching to the black one, which is the UV continuous fiber material. So in the end, the fiber mass can be molded through autoclave molding to evaluate the mechanical properties. And you can see even with recycled carbon fiber, we can still achieve 98 gigapascal tensile stiffness along the fiber direction. So apart from the mechanical properties, cost, and the sustainability, I would like to encourage all of us to think about whether there are any other potentials or benefits we could have by using the recycled fiber materials. So let's look at this graph, which is generally talking about the properties, the features of composite material. So if you're aiming for a very high mechanical performance, you need to go for continuous fiber prepreg or woven fabrics. But because of their contains the continuous fibers, you want to achieve very good formability. So if you want to get rid of the wrinkles and the fiber bridges, you need to think about the SMC and the BMC or the pellets. So the researchers and engineers are trying to develop a very good advanced material in this region, which can balance the mechanical properties and the formabilities at the same time. So is there any solutions from the virgin fiber material? We can have a look at this novel Toray product called ET40. It's slitting the UD fiber prepreg to make it contains short fibers. So if after compression molding, you can have a look at the cross sections of the composite sample. So if you use the UD prepreg around this corner, so you can achieve, you will achieve a large area of resin ridge. And if you use ET40, which contains lots of short fibers, so you can see all of the cross sections are fully covered by the fibers. So I would put ET40 at this area, so it can achieve better formabilities compared to the UD prepreg and slightly lower mechanical properties. But I was wondering, is it a cost-effective product? Is it can help us to apport into the circular economy? Why not just think about the recycled fiber products? It already contains lots of short fiber format. So I would introduce the allied tape matching with our request. So it can offer the superior SMC level formabilities and can be easily engaged with the rapid manufacturing process. As I mentioned, we can use compression molding, and it can offer the comparable mechanical properties to ET40 and its recycled product. So after this, I hope you have an initial image about the story of recycled carbon fiber composites recycling and reuse. Then we would move on to the glass fiber set. So lots of research work has been done by the advanced conscious group in the University of Strathclyde. So the similar first step is collect the waste pieces from the wind turbine blade, from the end-of-life wind turbine blade, and do the size reduction to make sure it can fit into the ACG's advanced optimized fluidized bed recycling process. So through a project called Recover, ACG developed the patent slicing to enhance the fiber strength and improve the bonding system. So with the regenerated fibers, you can say you only achieve 11% reductions on the tensile strength compared to the virgin fiber glass fiber products. So in the end, the recycled glass fiber has been molded and manufactured to wind turbine blade, and finally be used, reused in the renewable energy industry. So after all this information, LMC has already started to work with the world-famous researchers from the University of Nottingham and the ACG University of Strathclyde. We have already developed and submitted a proposal to the recent closed General Innovate UK Smart Grant, and I will let you know the details about this project if when we successfully be funded. So we are also very welcome to all the researchers and the industrial partners to join us and developing the project plans to close the loop of the composites manufacturing and moving forward to the circular economy. Thank you, everyone. I will hand you back to Iain.
Thanks, Joe. Thank you. So please find our contact details here. We're more than happy to catch up offline if you've got any particular questions. But I think now is the kind of time to go to the Q&A. So I know we've had a couple of questions coming in, which I'll just read out loud now and try and answer those. So a question from Jacqueline McNulty, which I think is a very relevant question, not just for Jacqueline, but for everybody online. So it's asking, so Jacqueline works with an advisory role with several startups. How do you choose which companies to support? Well, we're really happy to engage with any companies. I think it's really a question of value add. You know, if we think we can really add some value to the particular challenge that you have, then we'll find a way to get engaged. There's a number of ways that we can do that. So we can be directly funded, so we can work on a subcontract basis for that. We also work with, we're more than happy to work in collaborative R&D space as well. So as I mentioned on the case with ActBlade, you know, it's a really good way for companies to leverage the funds they have and to bring us on as a fully funded partner for that. So we're funded by a third model, which means we get a third of our funding from local authorities. We get a third from industry and a third from Catapult. So the Catapult funding enables us to develop some of these technologies on our own, so that we are keeping ahead of technologies, so that we were continuing to refresh our portfolio of products and services that we can offer. And then it's the industry engagement that and the academic engagement that really helps kind of pull and push that technology into the marketplace. So we're very flexible in the way that we work. So if you've got no matter whether it's an SME or a large prime, we are we'll engage at any level. So I hope that answers your question for that.